This is Unit 14, Solution Chemistry, Part 1 Notes. By the end of this unit, you should be able to describe the unique role of water in chemical and biological systems. You should also be able to distinguish between types of solutions, such as electrolytes, non-electrolytes, unsaturated, saturated, and supersaturated solutions. You should also be able to investigate the factors that influence solubility and the rates of dissolution, such as temperature, agitation, and surface area. The molecular formula of water is H2O, so you have two hydrogens bonded to one oxygen. This is an extremely important part of life because it covers over 70% of the earth, and most solvents in our body fluids utilize water. Hence, if we don't drink any water, we become dehydrated, and that could cause serious complications. Water can also exist as a solid, a liquid, or a gas in nature, and most of the time it remains in liquid under most conditions on Earth. Water also has a very high boiling point compared to other small molecular compounds. It has a very high specific heat. We investigated this in unit number 13 with thermochemistry, and it also has a very low vapor pressure. So all of these important properties of water allow it to be the most useful type of solvent or liquid that we can utilize today. The molecular formula of H2O also involves hydrogen bonding. This creates something known as surface tension. So whenever you see small critters able to walk across water, they don't necessarily walk on top of it, they just don't break the surface of water because you have multiple hydrogen bonding, so that's your hydrogen to an NO or F, so in this case it's an oxygen, and it creates this network system of water molecules. If you add a surfactant, such as soap, it can interfere with the hydrogen bonding. They're really long type of molecules, and they block the OH bonds or the interactions between the water, so then the little critters or the lightweight substances, they cannot quote unquote walk across water because there's no surface tension, so the surfactants break that. The molecular structure of water is also extremely important because it has differences in electronegativities between the O's and the H's. So water creates this polar molecule because you have a separation of partial positives and partial negative charges. Remember, oxygen has the highest electronegativity compared to the hydrogens, so you're going to have all the electron density pulled to the direction towards oxygen, so we're going to have a separation of a negative and a positive charge. And we learned about polarity last semester. So you need to keep in mind the partial positives and partial negatives of water. As I stated previously, water can exist as all three states of matter, such as a solid, liquid, or a gas. However, the orientation of the water molecules are different due to their different states, such as the water molecules are more tightly packed in the liquid phase than they are in the crystalline solid phase. So what happens is when liquid water freezes, they orient themselves to where there's much spacing between those atoms due to the hydrogen bondings. And the more space that you have, if we look at our density equation, the more space means the higher volume. The higher the volume, the lower the density. Hence, our solid water or ice has a lower density than our liquid water. And that's an important concept because ice floats in water, and that helps preserve the different climate or the systems, aquatic systems within these cold climates. Because if the ice didn't freeze and it didn't go to the top, then it would always go down, and then every single liquid lake or ocean or anything would freeze and everything inside of it would die. So we need to remember that our solid water or ice is less dense than our liquid water. Hence, that's why ice floats on top of water. Water is also commonly used as a solvent. That is what is dissolving the different solids or even gases. But solvents are used to dissolve. They do the process of dissolving. Water is known as the universal solvent because it can dissolve most substances within this entire world. That's due to its polarity. Again, we talked about polarity. There's differences between the oxygens and the hydrogen. So you'll have an overall negative charge, partial negative charge on the oxygen, and you'll have a partial positive charge splitting apart that molecule. So how water dissolves different substances is that the partial positive and partial negative surrounds the other positives and negatives, whether it's partial or just an ionic in nature. So for example, if I'm trying to dissolve sodium chloride, sodium has the +1, chlorine has the -1, hence you have orientation of the sodium chloride crystal, positives and negatives. But the positive sodium is going to be surrounded by the partial negative charge of your oxygen, hence you're going to have that interaction, as well as the partial positives of the hydrogens are going to surround the negative charge of your chlorine. So it's extremely important that there's these partial positives and negatives because that allows the pulling apart of a polar or charged molecule because they have similarities within their structure. Whenever water is used as a solvent, it can dissolve different substances, and that will make what is known as a solution. So whenever we saw the AQ, your aqueous solution, that is when a solid is dissolved in water. So the dissolution is the process by which one substance, known as the solute, is dissolved in another, called the solvent. So your solute is the dissolved particle in a solution, and then your solvent is the dissolving medium. So for example, if you're trying to put NaCl into water, salt would be your solute, and then water would be your solvent. And then the solution is made up of the solute and solvent, which is a homogeneous mixture that consists of both the solute and the solvent. The solvation is just the process that occurs when solvent particles surround the solute particles to ultimately pull the solid apart to form that solution. So in the previous slide, I had an example of sodium chloride where it orients itself based on the charges. And then the solvation process is whenever the water, due to its polarity, was able to surround the positive ion with its partially negative oxygen and to surround the chlorine with its partially positive hydrogen side. So the solvation is this process of pulling apart the NaCl into its individual ions, because after the dissolving process, what you have left in water are just ions. So it's not a chemical process occurring, it's the splitting apart of the NaCl molecule. And this is due to the fact that the attractive forces between the solute and the solvent are stronger than the bond that's trying to hold together the sodium chloride or your solute. So what we need to take away from this is just a couple of key terms where the solute and solvent, the solute is dissolved in the solvent, which makes the solution. The dissolution is the process of dissolving, but the solvation is the process of how the solvent surrounds the solute based on similarities and polarity. The reason why water can dissolve most substances is due to the fact of its polarity. And we're going to follow the solubility rule of likes dissolve likes, where polar substances or polar solutes are dissolved in polar solvents. So for example, salt and water. Salt's ionic and it's polar. Water is also polar. Nonpolar can dissolve in other nonpolar substances, such as diatomic chlorine. It is nonpolar due to no differences in electronegativity. Carbon tetrahydride, same thing. You have 4 hydrogens around it. There's no difference in the electronegativity. So both of those are nonpolar and they can dissolve in each other. But if you try to dissolve polar and nonpolar into each other or mix them together, such as oil and water, they won't mix because oil is nonpolar while water is polar. And you will see a distinct line or a separation because they will never mix. You can stir that solution completely for 5, 10, 15, even all day long, but once you settle out the particles, they will separate because they do not dissolve in one another. So we have to remember that rule, likes dissolve likes. So polar into polar, nonpolar into nonpolar. There's also solubility rules that we can follow, and as a pre-AP class, you are responsible for memorizing these solubility rules. You need to memorize this chart, and it's going to take a while because you have to get used to how to read it. So for example, if I'm trying to determine the solubility of NaNO3, that's your sodium nitrate, I would look at this chart that I have. So this first section here is the soluble compounds will contain these different types of ions, and then the exceptions to that. So if the soluble compound is bonded with its exception, then it's going to become insoluble. So how do I read this chart? Well, look at NaNO3. I'll look for my nitrate. It's in the soluble section. There are no exceptions to that rule, So NaNO3 will be soluble. And if you try to dissolve it in water, it's going to form an aqueous solution. That's what the AQ stands for. Then your next example that we have is AgCl. So I'm going to look for the anion. You always look for the anion, guys. Chlorine is in the soluble section here, but there's 3 exceptions. If it's bonded with a silver, lead, or mercury. In this case, chlorine is bonded to the exception, so the soluble substance will turn insoluble and it will completely stay solid. And then we have our last example, MgOH2. Well, the hydroxide OH is in your insoluble section. However, there are exceptions to it. If it's bonded with a strontium, barium, calcium, ammonium, or any of your 1A, so your alkali metals, which it's not because magnesium is in group number 2, but that one's not listed. So this insoluble substance will stay insoluble and it'll completely stay as a solid if you try to dissolve it. Factors that influence the rate of dissolution or how fast a substance dissolves includes these 3 examples. So whenever we're talking about the rate of dissolution, we're talking about how fast can something dissolve. Temperature affects the rate of dissolution because at higher temperatures, the kinetic energy of water molecules is greater, which allows for a higher frequency in collision, which will then allow for more solute to be dissolved. So it can also affect the amount and it can increase the rate of solubility. So temperature can affect the amount of solute that's able to be dissolved, and it also decreases the time that takes a certain solute to dissolve at a given temperature. So you can dissolve something faster. So if you want to dissolve something faster, heat it up. Agitation is a process of shaking, stirring, or mixing a solution. This one does not affect how much solute is able to be dissolved, so you can't stir and think you're going to dissolve any more, but it can make the rate of dissolution faster, so you're going to decrease the time it takes to dissolve a certain amount of your solute because you also have increased collisions because you're moving around the solvent. And then your surface area. The more surface area your solute has, the more chances the solvent particles will collide with the solute. Again, this one does not affect the amount of solute that can be dissolved, but it does make the dissolving faster. So you can decrease the time it takes to dissolve a certain amount of your solute in a given solvent volume. So again, temperature, agitation, and surface area can all decrease the time it takes to dissolve something, except the only one that affects the amount is going to be your temperature. There are different types of solutions, and the first 2 that we're going to talk about are electrolytic and non-electrolytic solutions. An electrolytic solution is a solution that has the ability to conduct electricity because the solute will ionize in solution. So it's going to contain electrolytes, which are ionic compounds. So like sodium chloride, NaCl, magnesium sulfate, MgSO4, anything that's ionic. So you have to have a metal and a nonmetal dissolved in water. Whenever it dissolves, it's going to ionize or break apart into different ions. So you'll get Na plus and Cl minus, or Mg2 plus and SO4 2 minus. And they will allow for the transmission of electrical charge. A very strong electrolyte will ionize completely, and then your weak electrolytes will only ionize partially. You don't necessarily have to know the differences between strong versus weak electrolytes at this point. Just know that a strong electrolyte, such as sodium chloride, will ionize completely in solution. And then your non-electrolytic solutions do not conduct electricity because they do not ionize in water. So these are going to be like your molecular or covalent compounds. So for example, if you have sugar, there's no metal in this compound. There's no metal in chlorine or carbon dioxide. They're all covalent or molecular compounds. They're non-electrolytes, and they will form a non-electrolytic solution. So if you compare strong versus weak versus a non-electrolyte, strongs are able to conduct electricity. Weak ones only partially conduct. And then your non-electrolytes do not conduct any electricity whatsoever because the non-electrolytes do not ionize in solution. Okay, so the last 3 types of solutions, so we had electrolytic and non-electrolytic. Now we have unsaturated, saturated, and supersaturated. An unsaturated solution is a solution that contains less solute than the maximum amount in a certain amount of solvent at a given temperature and pressure. So this means it's underneath that maximum amount. Your saturated solution is a solution that contains the maximum amount of solute that it can dissolve at a certain volume at a given temperature and pressure. So saturation is at the point where you cannot dissolve anymore. And then your supersaturated solutions are a solution that contains more solute than it can theoretically hold at a given temperature and pressure. And that's because you heat up that solution and you can increase the amount that you can dissolve. So go back to the factors that influence the rate of dissolution. Temperature is the only one that can increase the amount that you can dissolve. So whenever you're looking at a solubility curve, saturated is on the line, supersaturated is above the line, and then unsaturated is underneath the line. So how you would be able to read these types of curves, if we look at the problems to the right, your solubility unit is on the y-axis, your temperature is on the x-axis. So if you're asking how many moles per gram, so that's your solubility unit, of potassium chloride, KCl, can be dissolved at 40 degrees Celsius. So what you have to do is look for the KCl line, which is your orange one down here. It is, let me get the orange then. So your orange KCl, you have to go to 40 degrees Celsius, which is here, and you just make a line up. I know it's kind of curved, but do the best you can to go straight up. You're looking for how many moles per gram. So once you go up and you hit that line, you go over to the y-axis here, and it's going to be about 4 moles per kilogram. And I know my lines are kind of messy, but if you can just make a straight line with the 4 going up over here and the 5 going across there, then it should be about 4, give or take 1 mole per kilogram. I know these aren't going to be the most accurate answers, but do the best you can. The next one is asking which compound has a solubility of about, let's see, 15 moles per kilograms at 60 degrees Celsius. So again, we need to go to our 60 degrees Celsius, just make a line straight up, do the best you can, and then you look over at the 15, we make another line. Oh, so this is the only one that's really close, which is going to be our sodium nitrate. So that's its solubility. And then the last question is asking what type of solution, when I say type of solution, I mean saturated, super, or unsaturated, do you have if you dissolve 5 moles per kilogram of sodium chloride, so this is going to be our NaCl, which is the pink or the pinkish purple looking one, at 20 degrees Celsius. So you go to 20 degrees Celsius, you make a line, the best you can, and then you look to see what type of solution if you dissolve 5. So your 5 is right here, give or take an area, but if you compare it to that purple or pinkish purple line, it's underneath the sodium chloride line. So if you're underneath, you would be an unsaturated solution. If you're hitting that line exactly, so at 20 degrees Celsius, if you have about 6 moles per kilogram, that would be your saturated. And then say, for example, you try to dissolve 20 moles per kilogram of your sodium chloride at the same temperature, that would be a super saturated because you're way over that line. So saturated is on the line, supersaturated is above, and unsaturated is under the line. And you'll be practicing these solubility curves in class after this lecture. All right, so have you accomplished these objectives? If not, please make a note of any of the information that you don't understand, or ask me in class for the next lecture, or come after school for tutorials if you need any more clarification.